And the reason for that is we are just going to complete one important concept that is related to the T1 and T2, T2 star that we were talking about, and to do with recording the signal, right? Your decay signal in relation to application of excitation pulse. What we covered so far is if I apply pi by 2 pulse, I get the maximum signal, and all our illustrations that we have shown, we have pushed it to the floor, allowed it to dephase, record the signal, and this is a T2, T2 star, T2. No, there are two relaxation times involved. So the decay in the free induction decay that you saw, right? It started with a maximum value, and then with the time it decays. Initially, it decays faster due to the T2 star effect, and then it continues to dephase due to T2 effect, and then eventually the signal goes to zero. On the other hand, the MZ component increases. So your T1 due to T, which we called as T1 relaxation time. Okay. So now the question is, I can play this game every time. I can allow the excitation, push it down, record the signal, no issues. But now the question is, there's one more capability that we can do that will allow us to notice this T2 or T1. Both of these are also characteristic of the material, right? Or the sample volume. So if you're talking about hydrogen, if the neighbors are slightly different at that location, then you're going to have a different T2, right? And so also depending on the loss, you're going to have different T1. So different locations, depending the volume that we started with, which had the signal, had proton density. So the signal that you are getting, one is the characteristic of the material with respect to having the proton density that is dictating your value of M. Now, in addition to that, we have talked about the decay the relaxation time itself is a characteristic of the sample material. Okay, so there is T2, and then there is T1. That is also sample's ability to lose, right? Some material lose fast, and then they come back to the equilibrium faster. It has to do with the energy loss. So this is also a material problem. So now we have different material properties, which is all somewhere there. But how do we measure this at each location? That is going to be the challenge that we are going to talk about. So in order to do that, we already understand that we need to have flexibility in pushing this down, recording how fast we push, how many times we push. All these are parameters that is under your control. You have the ability to on the excitation pulse, off the excitation pulse. How long do you want to on? How frequently you want to on is all in your control. So therefore, there is another important concept or one important tool, right, to play this game you have, which is I have I have a signal which is transverse. I know the signal is coming only from the transverse component. Now we talked about dephasing, so the signal is going down. So what happens if I want them to rephase again, right? How do I make it rephase again? One way to do it is, well, what is the meaning of this dephasing? Some is going, right? Remember, why is it dephasing? Because some nucleons, some vectors, some nucleus are moving faster, some are moving slower, slightly up and down the Larmor frequency. So what happens is they start to move away from each other. So now if I give another command, right, and say, oh, whoever is moving fast, you start to slow. Whoever is moving slow, you start to move fast. If I give that command, right, if I know how to do that, then what will happen? The slow ones will start to move fast, the fast ones will start to move slow, and therefore after you tell that command, within few time, they'll start to become coherent again, right? Again, after you finish that command, they will have their own ability to dephase again. But the point is, by having additional command, I can make them come to coherence again. What does that coherence as? What does that command have to do? That command has to do with making the faster ones to slow down and the slower ones to fasten up, right? Then I can do it. So how do I implement that command? Now you recall we talked about, of course you have to apply excitation pulse. I mean, you have to have additional excitation pulse. That's a given. So now the question is, how will you apply the excitation pulse, or how long will you are already on the floor, right? What are you going to do? If I apply another 90-degree pulse, it will go down. No transverse component. So it doesn't make sense. Right? So what will I do? So this is where the other pulse that we talked about, right? Pi pulse. First is pi by 2 pulse. Then we talked about pi pulse. Now you say you start here. If you apply pi pulse, what will happen? There should be a 180 degree shift. What does a 180 degree shift means? It's all still going to rotate in this direction. But what is 180 degree going to do? It is going to essentially change the polarity. So whoever is going fast has to come down, whoever is going slow has to fasten up. It will achieve the effect, right? So we are going to talk about formation of spin echo. Formation of spin, you know, that is what we have covered so far. The new term here is echo. What is an echo? Echo is a reflection, right? You have a signal. Echo means is a repeat of the signal, a poorer cousin of the signal. That is what is an echo. So that means spin echo means I have a signal from spin. Spin echo means I have a signal from spin echoed again. Meaning I have the signal. It is trying to signal is going to go down. I am trying to make it come back and record it again. So that is your echo of the signal. So by applying 180-degree pulse, the dephased spins can recover their coherence and form an echo signal. So here is the completion of the time sequence that we had. So initially we had time, so you did the pi by 2, all of this is in the rotating frame of reference. So you have z dashed is pushed down because of pi pulse. After the first RF excitation, pi by 2 excitation, it starts to dephase. You allow time, it starts to dephase completely. But sometime after that, you apply another pulse, 180-degree pulse. Now, if you do this 180-degree pulse, it will essentially move it to the other direction. It is in this direction. You are applying 180-degree means it is going to go to the other direction. So when it goes to the other direction, what happens? The slower one tries to become fast, faster one becomes slow, so it is trying to catch up. So it is trying to come together, and therefore you are going to have again some coherence. Notice that the coherence here is not as good as the coherence here, right? Here you see it's a single arrow which kind of says that everything is coherent, whereas here you see it's almost coherent, but it is not single line. It is all trying to achieve coherence. So signal is increasing, but it is not as great as this one. Also notice you started with this circle, right? This is your amplitude or magnitude, this radius. The radius is also reduced. So that means why? Because it is relaxing. There is a T2 process, right? So it is relaxing. Signal is relaxing. So there is a loss in signal. That's why this arrow is reducing. Eventually this arrow will go to 0 in the XY, right? It will only be Z component. So what you have done is, by doing this, you have tried to recover the signal as much as possible. It's not complete, but you have gained the signal. So it is going to be a copy of your original signal, but going to be slightly lower than that. So if you want to see the animation, right, that will give you, so initially excitation, you have the signal, red and blue signifies, fast and slow. For example, it is going, it is dephasing, some are fast, some are slow. Now after I apply 180-degree pulse, the slow becomes fast, fast becomes slow. So that means they are all trying to regroup. It is not as great. So now its signal starts to build again. The signal starts to build again after your excitation, 180-degree excitation, right? 90-degree signal starts to decay. I apply 180-degree. After some time of application, it starts to form back. So my signal starts to come in. Signal builds in. So it goes up again. The nature has it that it will start to dephase again because you have switched off the excitation pulse, right? So the 180-degree pulse, excitation pulse, 180-degree excitation pulse makes it come together, and then when the other side it goes down, it starts to dephase again. So again, this will start to decay. So this is the signal. This is the signal, right? And what you are going to get is an echo of the signal. So 180 degree you apply, you get an echo of the signal. Let me stop here just so, yeah. So you get an echo of the signal. So therefore you have timings involved. So this is time to echo, right? So T2, we already talked about relaxation times, which are all material property. Whereas now you notice this time to echo is nothing, you have control. You know when you want to apply the excitation pulse, right? So you are applying time to echo. So this timing is also under your control. So the whole beauty of MRI is you have multiple parameters that is inherent to the material property. You can manipulate what you want to get of the material by changing that and the sequence in which you are applying the RF excitation pulse. So now in this case, I have applied echo signal. I will get an echo signal. I have applied a pi pulse following pi by 2 pulse after some TE by 2 time. So essentially you notice there is inherent contrast due to inherent signal due to material property based on T2 relaxation time, T1 relaxation time, and the proton density. How much of protons are there in that volume, right? So that is a material property. So that signal I can manipulate which aspect I want to see of that sample volume of that tissue. Do I want to see the T2 characteristics? Sure. Do I want to see the T1 characteristic of the tissue parameter, or am I just happy with how many protons are there in that given volume, right? Any of these characteristics of the tissue, I can manipulate the signal using the sequence of pulse that I am using. So this is what is called as a pulse sequence. The pulse sequence can be manipulated to get whatever aspects, characteristics of the material property you want. Namely here, at least in this limited discussion, we have 3 characteristics: proton density, T1, T2 of the material. We can exploit or understand, characterize, measure using your sequence of application of the excitation pulse, and of course the timing involved when you are recording, after how long you are applying. All these are parameters of acquisition. So just to complete, so we need some way to put all these together, which is called as a timing diagram or a pulse sequence diagram. Okay, so we will expand on this as we build the material. First is you have RF excitation. I have my MR signal. What I am measuring is going to be the echo signal. So I have to design the TE and TE by 2. So I need to build this. So this is called as a timing diagram and a pulse sequence diagram, because I know the sequence here 90 degree, and then I am giving 180 degree after TE by 2 to get a signal that is a echo signal. Okay. So that means I can manipulate. There are several sequence people have played with. So one is multiple pi can be created, and essentially what you are going to get is 90 degree, and then you are applying multiple pi's, pi by 2 first, pi. But notice each time your signal is not going to come back to the original level. Each time the signal is going to be poorer based on your T2 decay. Remember, it is all decaying. You are flipping it left, right, 180 degrees. But then this decaying and the TZ is trying to increase with its time constant T1, right? So this is your time to repeat. So the pulse repetition time. So I can that axis. So I can do 1 pi by 2 and flip it left, right multiple times. After I know that signal is decaying due to T2. So after 2 or 3 times the T2 value, no matter I flip it how many times, apply 180 degree anytime, the signal is going to be very weak, right? It is going to be very weak because the transverse component is lost. Your T1, your MZ is increased. So after some time, it is not worthwhile flipping it left right because it is inherently poor signal. So at that time, what I will do is I will again allow it to go back completely and then put the 90-degree pulse again. So time to hit the next 90-degree pulse will be called as pulse repetition time. So you notice this is just to illustrate that you can manipulate the pulse repetition time. You can manipulate whether you want echo signal, how many times you want the echo signal. All this can be manipulated. Essentially, you manipulate this with an idea to exploit whether you want to get the T2 characteristic of the signal, T1 characteristic of the material, or just the proton density is good enough, right? So all these can be manipulated using the pulse sequence diagram. So just to complete, we already had our Bloch equation for motion. When you had static, we added to the static field the excitation field also. We upgraded, right? Now the motion is due to not just the static field, it is also due to your rotating field. So we have to upgrade this motion equation to incorporate the effect. We know what the motion is. We saw it vividly in the animation, but mathematically this is how you complete. This is what is called as Bloch equations. We started with. It is going to have the magnetic field that we had B naught. Now this B of t also includes B1 of t, right? So M of t cross B of t had this. Of course, there is a relaxation. The magnitude of the magnetization vector changes due to the relaxation. The relaxation property is captured using your T2 and T1. So this is your relaxation matrix. So this is a complete set of Bloch equation which describes the motion of your magnetization vector in the presence of static field and the applied RF excitation field. Okay. There are a couple of examples in the textbook where he expands the vectors into components and shows for pi by 2 what is the mxy. So please have a look at that. So solving the previous equations in all the three different directions gives you the equations that we saw already. Okay, so just have a look at the textbook on this as well. I hope with this we actually complete the understanding of what is the signal origin, what is that we are recording, and how is the recording of the signal changes. The changes in the signal capture or due to the physical properties that we are going to go after, T2, T1 and proton density. How is that? So how do we manipulate all this to see T1 or a T2 or a proton density of that volume, right? Characteristic of the volume. That how we are going to do will be the topic of interest to us, which will be the next module that will be on contrast in MRI. So once we understand the contrast in MRI, then we will move on. Physics is complete. Then we will move on to how do we accomplish this using instrumentation and signal reconstruction.